final bit of the theory in this chapter of torque and angular momentum, the Newton's laws, how to build the Newton's laws for system of particle. For a particle, Newton's second law is defined as the net force is equal to rate of change of linear momentum. And for turning of the particle about a reference point, the net torque acting on the particle about that point is equal to rate of change of angular momentum of that particle about that fixed point. For the system of particle, we know that tau, the net torque about any point, reference point, ith particle, velocity vi, mass is mi, is given as Ri cross Fi. Fi is the net force acting on ith particle. If you take the center of mass somewhere here, Ri can be written as RIC plus RC. Ri can be written as RIC plus RC. Then you can write the net torque about this point as RIC plus RC cross Fi and summation of this. RIC cross Fi, summation of this plus RC cross Fi, summation of this. This is the net torque about O. This is the net force acting on ith particle. This is the position vector of ith particle with respect to the center of mass frame. Therefore, this is the torque experienced by the system due to the all forces about the center of mass frame. I write it tau c plus RC is a constant quantity. You pull it out, cross, you take this symbol of summation sigma inside, and this physically signifies the net force acting on ith particle. So tau c plus RC cross, this is the net force acting on the system, which is equal to sum of the net forces acting on all the particles. I call it F. Let it be F net. That is equal to the net torque acting on the system about the given reference point. This theory previously we deduced. And we have the similar type of expression for the angular momentum, which states that angular momentum about the point O is equal to angular momentum about C plus angular momentum of the center of mass about that given reference point RC cross M into VC. This is equation number 1. Since angular momentum about O is equal to angular momentum about the center of mass plus angular momentum of the center of mass with respect to the given reference point. Taking the derivative of both sides, we can write the rate of change of angular momentum of the system with respect to the given reference point is equal to a rate of change of angular momentum of the system with respect to the center of mass frame plus rate of change of angular momentum of the center of mass of the system with respect to the given reference point O. That is equal to dLc by dt derivative of this term, that is drc and dt cross mvc plus rc cross d by dt over mvc. Since this is equal to vc and vc cross vc is 0, the entire term will vanish. Then we are left behind with these two terms, rate of change of angular momentum of the system with respect to center of mass frame plus RC cross rate of change of linear momentum of the center of mass is none other than the net force acting on the system, supposed to be acting at the center of mass. That is equal to rate of change of angular momentum of the system with respect to the given reference point. This is equation number B. Since torque is equal to rate of change of angular momentum for any reference point, we can write tau O equal to d by dt of LO. Tau C is equal to d upon dt of LC. Then writing tau is equal to tau C plus RC cross F net force is equal to d LO upon dt is equal to dLc upon dt plus RC cross F net, and this factor is none other than the tau C. Or you can just compare these two terms and compare these two terms to get a pair of equations. Comparing both sides, we have tau C is equal to rate of change of angular momentum about the center of mass. This is one equation, and comparing these two, RC will be common, and we are getting the net force acting on the system is equal to rate of change of the linear momentum of the system. F net is nothing but m into AC, mvc is equal to m dvc upon dt. That's equal to m into AC. Therefore, we are getting two sets of equations. F net is equal to total mass times the acceleration of the center of mass. This is called Newton's second law of rotation. This is called Newton's second law of, or for translation. And combining with these two will give us Newton's laws for system of particles. For motion of system of particles, there are two types of motion, rotation and translation. When you call rotation, you should see whether the center of mass is moving or not. If you say rotation, you should see whether the system will possess a non-zero angular momentum with respect to the center of mass or not. Now we have put all the equations, all these ideas, the theoretical details of the system of particles, both rotation and translation. And to understand all these ideas, let us supplement through some problems as concluding examples. The Newton's second law of rotation states that the net torque or net torque of all external forces taken with respect to the center of mass is equal to rate of change of angular momentum with respect to center of mass. This is called Newton's law of rotation. And Newton's law of translation states that the net force or sum of all external forces, because sum of internal forces will be equal to 0, is equal to rate of change of linear momentum of the system, that is equal to mass of the system into velocity of the center of mass, or we can just write mass of the system into the acceleration of the system. Acceleration of which point of the system? Acceleration of center of mass of the system. This is called Newton's second law for translation of the system of particles.